Hello and welcome to the Chapter 5 podcast on Section 5.5. Today we're going to discuss calorimetry. Calorimetry is basically measuring the flow of heat. Um, we measure the heat flow by using a device known as a calorimeter. Um, there are many different kinds of calorimeters. Some are very simple, as what you see on the right here, where it's styrofoam cups nested in each other with water inside with cork stopper or some sort of lid with a thermometer and a stirring rod inside. And sometimes it could be much more complicated. This is a bomb calorimeter where inside the bomb, which is the little container you see here, is where the reaction takes place, and there's energy coming in, and then there's water inside this container that measures the change in energy that occurs. So these represent either ends of the spectrum. Heat capacity and specific heat are aspects of calorimetry that you're going to need to know. Heat capacity is measured by basically the amount of energy it takes to raise an object's temperature by 1 degree Celsius or 1 Kelvin. Notice that there's no limit in terms of how heavy or what the mass of the object is, which can be a consideration, which we'll talk about in a little bit. A little more specific form of capacity is molar heat capacity. Here we're talking about specifically 1 mole of a substance. Same kind of idea, so it's the amount of heat required to change the temperatures of the object by 1 degree or 1 mole's worth of a substance. There's another one that we used in honors chemistry last year if you had it. This was specific heat. They're using different symbols than we used in honors chem, so don't be confused by that. And this is the heat capacity of 1 gram of a substance. So molar heat capacity and specific heat capacity are basically more specific versions of heat capacity, where in heat capacity there's no consideration of the object's actual mass. You could be talking about a house or like a brick, whereas in molar and specific heat capacity you're dealing with specific amounts. Most of the calculations that we're going to do involve specific heat capacity. There's an equation that we use. So specific heat is equal to the heat transfer divided by the mass times the change in temperature. Or Q. We can rearrange this, and Q, if we're solving for heat flow or heat itself, it's equal to the specific heat times the mass of the object times the change in temperature. There are a lot of specific heats that have been standardized, so a lot of substances have specific heats that we can use for references. And we'll talk a little bit about the relevance of that in a moment. We can do specific heat calculations. This one involves using specific heats to calculate heat emanation. So let's say we have a 50 kilogram rock, and we have a change in temperature by 12 degrees. This is an increase in temperature. So, and then of course in order to do this you need to know the heat capacity of the rock, or specific heat capacity of the rock, which is 0.82 joules per gram per degree or per Kelvin. So we can use our Q equals S times M times delta T. We substitute in our values, so 0.82 for our specific heat. The 5 times 10 to the 4th represents the mass, and the 12K is the change in temperature. Again, since we're doing temperature differences, it doesn't make a difference whether we're in degrees Celsius or kelvins in this case. And so we figure out that there's 4.9 times 10 to the 5th joules of heat absorbed by the rock. If we continue along this line, let's say we can also use this equation to solve for other things besides for heat. So sometimes we can solve for temperature or mass, or if we don't know the specific heat. So in this next example, we're solving for temperature change. So let's say the rock gives off 450 kilojoules of heat. We can figure out the temperature change associated with that heat loss. And we rearrange the equation doing some fancy algebra, and we end up with Q over S times M, and we can substitute our values in, and we see that if 450 kilojoules are given off by the rock, the temperature would change by 11 degrees. either Kelvin or Celsius. Constant pressure calorimetry. The idea behind this is that water solutions um, gain heat from the reaction itself. So the concept behind calorimetry is that the energy given off by the substance will be absorbed by the water. Okay, and so the heat flow will go from the substance to the water if it's heat given off. Okay, so it can go in a couple different directions depending upon the nature of the substance and the direction of the heat flow. So if heat is lost by the solution, that means that the reaction is gaining heat. If the heat is being lost by the reaction, then it's being gained by the solution. I know it seems kind of confusing, but we'll talk about this in more detail in class. But the heat of the solution is going to be equal to the specific heat of the solution times the mass of the solution times the change in temperature. So the reaction, if this is these will be equal and opposite to each other based upon energy flow. Okay, and most of the time we're going to assume that the water solution has the same specific heat of water, because we're going to assume that the solutes don't contribute much to any significantly to the heat flow. And it allows us to kind of simplify some of the reactions as well. So how does this actually work in calculation? Well, here we're using a coffee cup calorimeter, and we're actually going to do a lab like this later after this lecture sometime. So let's say we have 50 milliliters of a 0.1 molar solution of silver nitrate, and we have 50 milliliters of a 0.1 molar solution of hydrochloric acid, and let's say we mix these together. Now remember, when we mix these together, the new volume is going to be 100 milliliters, right? And as we mix these things together, the temperature of the water solution increases from 22.3 degrees Celsius to 23.11 degrees Celsius. We want to calculate the change in enthalpy in this reaction, and we're going to assume that the solution has 100 grams, has a mass of 100 grams, and this is based on the density of water, and then the specific heat is going to be equal to that of water itself. Okay, so a lot of assumptions that we're making here. This is the summary of our reaction. So as we mix these two things together, we're going to get a precipitate and nitric acid. Okay, the idea behind this is that as this reaction gives off energy, the water is absorbing the heat, which is the reason why we see the temperature increase. So if we figure out the temperature increase of the water along with the mass of the water and the specific heat of water, we can figure out how much energy the water absorbed. And remember, that energy that the water absorbed came from the reaction itself. So if we know what the Q of the solution is, then we know the enthalpy from the reaction. So the heat of this gained by the water solution is equal to the specific heat of water times the mass of water times the change in temperature. So 4.18, because we're assuming that this is mostly water, 100 grams, and then the difference in temperature. So this represents the amount of energy absorbed by the water. And we agree that if this was absorbed by the water, it means it was released by the reaction. So with respect to the reaction, if that's the system, that's going to be a negative mathematical value. Once we have this, we can go back and we can figure out the enthalpy of the reaction with respect to the moles of AgNO3. So do you see how in delta H is kilojoules over moles of AgNO3? So we can convert this 338.6 joules to kilojoules by dividing by 1,000, but we have to come up with the denominator, so we need to figure out how many moles of AgNO3 there are in this solution. So to get that, we multiply the volume times the molarity of the solution. So remember, the original molarity was 0.100, and liters cancels, and this is how many moles of AgNO3 are present. So if we divide our answer from the first part by the moles of AgNO3, we get negative 600 67,700 joules per mole. We divide by 1,000, that becomes negative 67.7 kilojoules per mole. I know it seems kind of confusing, but it's drawing in a lot of different things from previous chapters that we're combining here. So these are things that we'll work on in class, and hopefully will make it a little bit more sense, because we'll work on these together to make sure you understand what's going on. Bomb calorimetry is usually specific for combustion type reactions. It's also considered constant volume calorimeters. These bomb calorimeters, the sample is placed in the bomb, and the same, just like with the coffee cup, the water is going to absorb the energy as the reaction takes place. Because during combustion reactions, heat is always released. The heat of the reaction will be equal to the heat capacity of the calorimeter times the temperature change, and usually they'll figure out for this object what the heat capacity is, and then you can just look at the change in temperature. The heat transfer here is internal energy rather than enthalpy, although the difference actually is less than 0.1%, so we more or less treat them as the same thing. We won't really use bomb calorimeters ever, but it's just something there for your own information. Let's say we're doing a bomb calorimeter calculation. So here we have our organic sample. We have this many grams of it. We burn it in a calorimeter. This is the heat capacity of the calorimeter. Every calorimeter will have a different capacity, so that's why they give it for this. The temperature increases this for the water, or for the calorimeter, and we're going to calculate the heat of combustion of lactic acid. So it's going to be, we're going to do kilojoules per gram and kilojoules per mole. So we'll have two different answers. Okay. First thing we need to do is we need to figure out the heat given off by the reaction. Now remember, once we figure out the heat absorbed by the calorimeter, where that's equal to the heat released by the reaction. So for this one, it's the capacity of the calorimeter times the change in temperature, which is shown here. So this is how many kilojoules are given off by the reaction, and we already have grams of our sample, which is lactic acid, and the second part is to convert to moles of lactic acid, because we're going to need two answers. For the per gram answer, we take our kilojoules of heat and we divide it by the original mass of the sample, giving us this for our per gram answer. And then the heat of combustion per mole we divide by our mole converted answer. And so they're basically the same thing. It's just represented in two forms of mass. And again, we'll do some of these in class as well. So hopefully this won't seem so confusing. Until next time, I will see you.